So we can also take what we learned from this small example and extrapolate it out to a larger sample, generally speaking, of size n. Okay? So let's say we want the likelihood function for a Poisson distribution. Okay? That likelihood function, which contains y1 all the way to yn, and our parameter lambda, okay? That's equal to that probability function evaluated for each one of these. So that would be lambda to the y1 e to the minus lambda divided by y1 factorial. Okay? We're going to multiply that by lambda to the y2 e to the minus lambda over y2 factorial. And then multiply that by lambda to the y sub n e to the minus lambda over y sub n factorial. Okay, so that's our likelihood function for a sample of size n that we think was pulled from a Poisson distribution. And we want to know if it indeed was pulled from a Poisson distribution, what's the optimal value of lambda that would maximize the likelihood that we did pull those n observations. Okay, so we can rewrite this as this would be lambda to the sum of y sub i's. Okay, so remember what we do if we're multiplying lambda or a value raised to a power, we multiply that several times over. We're just summing up those powers and putting them here. Okay, so lambda to the y sub 1, lambda to the y sub 2, lambda to the y sub n is just lambda to the y sub 1 plus y sub 2 plus y sub n. Okay. Then here we've got e to the minus lambda multiplied by itself several times. We could rewrite that as e to the minus n times lambda. Okay, n times over, we've got that. Okay, and then in the denominator, we've got what? Y sub 1 factorial times y sub 2 factorial times y sub 3 factorial and so on up to y sub n. So that's the multiplicative sum of y sub I factorial. Okay, y sub 1 factorial times y sub 2 factorial times all the way up to y sub n. So we've got this multiplicative sum from I equals 1 to n. This sum is I equals 1 to n. Okay? And then we could rewrite that, just so we're clear, as lambda to the sum of y sub i's multiplied by e to the minus n times lambda multiplied by, let's put this up here, that is the multiplicative sum of y sub I factorial raised to the negative 1. Okay? So now let's take the natural log of this so we can ultimately take the derivative. So we want to take the natural log of L. Okay? That's the natural log of each one of those added together. So that's the natural log of lambda raised to the sum of y sub i's plus the natural log of e to the minus n lambda plus the natural log of the multiplicative sum of y sub I factorial raised to the negative 1. Okay? So then we could rewrite this as, we could bring this out front, right? So that's the sum of y sub i's times the natural log of lambda. And then this would be the natural log and the e canceled out, so that's just negative n times lambda. Okay, and then here we have the negative 1 that comes over here, so that's just the negative of the natural log of the multiplicative sum of y sub I factorial. Okay, so now all we have to do is take the derivative, set the derivative equal to 0, and solve for lambda. Easy. So partial derivative with respect to lambda of the natural log of L is the partial derivative of this with respect to lambda. That's just the sum of y sub i's over lambda. The partial derivative of this with respect to lambda is just minus n. The natural log of, the derivative, partial derivative of this with respect to lambda is 0, because there's no lambda in here anywhere. The derivative of this with respect to lambda is just 0. So this is our derivative. We set it equal to 0, and we solve for lambda. Okay? If we do that, we got the n over here, multiplied by lambda, divide by n. We've got lambda is equal to the sum of y sub i's over n. Okay? So the general form, if we've collected n observations that from what we believe to be a Poisson distribution, and we want to find what the optimal value of lambda to maximize the likelihood that we did pull those observations from a Poisson distribution, the general form is just the sum of the observations, the sum of the counts in this case, divided by the number of counts, the total number of observations. So the sum of y sub i's over n. And of course, we're summing from I equals 1 to n. Okay? This would be the optimal value of lambda. This would be our maximum likelihood estimate for the value of the rate associated with this Poisson distribution.